Welcome to the chemistry question. Jordan here, and today I'm finally getting to the video I've been avoiding because of the overwhelming amount of important information there is to cover. This video is about carbon. Carbon is the fourth most abundant element in the universe after hydrogen, helium, and oxygen. It has three natural isotopes, carbon-12, carbon-13, and carbon-14. Carbon-12 is stable and is by far the most abundant element of the three isotopes. Its atomic mass, by definition, is exactly 12, as one atomic mass unit, or Dalton, is defined as 1/12 the mass of a carbon-12 atom. Carbon-13 is also stable but much less abundant. Carbon-14 is radioactive, decaying by emission of a beta particle to nitrogen-14 with a half-life of 5,730 years. Carbon-14 is thus used in carbon dating. No, not that kind of dating. There we go. By studying radioactive decay of the carbon in a sample compared to the sample from a known date, and with the knowledge of carbon-14's half-life, scientists can fairly accurately determine the age of any sample back about 10,000 years. On to carbon's chemistry. Carbon has 4 valence electrons, which means it will make 4 covalent bonds to form an octet and be stable, as seen in this model of methane. This also allows it to form long chains of molecules, for example, the fatty acid tails of this phospholipid. As one could imagine, this flexibility in bonding yields so many possibilities for compounds, even to the point of creating life. Just as an example, humans are made up of about 18% carbon by weight. Oxygen is greater because it is heavier than carbon and is the largest component of water by weight. A whole field within chemistry is solely dedicated to the properties of carbon, and it is known as organic chemistry. Organic chemistry deserves a whole separate series of videos, so I will not go into it here. Even the properties of the element itself, forgetting the compounds, are still amazing. Carbon has more allotropes than any other element, even more than sulfur, and these allotropes are incredibly diverse. We will start with coal, an impure form of amorphous carbon. We mine it, ship it in large quantities, and then burn it to release energy that powers our lives. The only downside being that burning coal produces immense quantities of carbon dioxide that are released into the atmosphere, contributing to climate change. Another allotrope of carbon is graphite. With graphite, carbon forms a honeycomb lattice of hexagons stacked in many layers. Graphite is very soft, somewhere between a 1 and a 2 on Mohs hardness scale. This softness makes it a much less toxic replacement for lead in modern-day pencils. Another interesting property of graphite is its diamagnetism. Diamagnetic specimens repel and are in turn repelled by magnetic fields. Because of this, a thin sheet of graphite will float over rare earth magnets. Another allotrope of carbon is diamond. Diamond is everything graphite is not. Whereas graphite is dark gray to black, diamond is colorless. Diamond is an electrical insulator, yet graphite conducts electricity. Graphite is made up of hexagonal sheets, while diamond has a pure middle crystal structure. Finally, graphite is one of the softest materials known, while diamond is one of the hardest. Diamonds are also incredibly valuable, not so much because of rarity, but because they are incredibly difficult to work with as a consequence of their superior hardness. The price is justified, though, because a diamond is forever. Unless, of course, you let the diamond get too hot, at which point it reacts with oxygen and becomes carbon dioxide gas. Oops. A final interesting point about diamonds. It has been discovered that solid diamond floats in liquid diamond, which is a fairly rare property. This must have been incredibly difficult to test, as one would need a pressurized chamber to prevent sublimation, an inert atmosphere to prevent oxidation, several thousand degrees Kelvin, as a diamond has a higher melting point than any other element, and some way to keep that liquid diamond from melting everything else. I couldn't find an image of the diamond experiment, so this picture is actually just ice cubes of water. Recently, more allotropes have been discovered, all with fascinating properties. Buckminster fullerenes, or buckyballs, contain 60 carbon atoms arranged in a sphere, with an appearance not unlike that of a soccer ball. Nanotubes are long strands of carbon in a cylindrical layout that have incredible strength. Finally, in 2010, the Nobel Prize in Physics was awarded to a group of scientists who took this to some graphite, peeling off layer by layer until they were left with a crystal lattice 1 atom thick. This new allotrope of carbon, graphene, is very strong and has many possible uses in the electronics industry. There is so much more to cover on carbon. We have barely scraped the surface, and I will continue to post more videos about it. Thank you for watching the chemistry question. Be sure to subscribe, leave any questions or suggestions in the comments below. Until next time.